Greetings, everyone. In this lecture, we are going to begin our discussion of the Modflow groundwater model, which will be the primary focus of our work for most of the rest of the semester. And there's a lot to talk about when it comes to Modflow, so we're going to have three separate presentations to talk about the different components. In this presentation, we're going to talk about the primary organization of Modflow and the main required packages or subcomponents. And then we have two separate lectures we're going to do on the optional packages or features of Modflow. So buckle in. Here we go. We are now at this stage in our model development process. Code selection is where we decide which model to use. Well, we're going to use Modflow. That part's easy. Model design is where we take our data associated with the main features we've defined in our conceptual model, and we actually build and run our numerical model. And this is basically amounts to preparing the input files describing the geometry and properties of our aquifer and the stresses, the sources and sinks, and then launching Modflow to run that and then viewing the results. We're going to use a graphical user interface that will really facilitate that and make it much easier, but that's what we're talking about, building the numerical model. So let's do a quick overview of some primary features of Modflow. It's developed by the United States Geologic Survey, and the first version of Modflow was released in 1983, so it's been around for a long time. It is a public domain model and open source, which is one of the reasons it's so widely used, and certainly the most widely used groundwater model in the world. It's not just the United States, but the world over it seems to be the dominant groundwater model. It can be used to model both steady state or transient, primarily saturated flow, although there is a package associated with Modflow where you can actually simulate flow in the vadose zone as well, but it's the main part is used for saturated flow. There have been a number of versions of Modflow over the years. There was a major release in 1988, 96, 2000, 2005, and then there was a release of a version of Modflow called Modflow NWT. We'll talk about that a little later in the semester when we talk about solvers. It has a Newtonian solver. And then more recently there was an unstructured grid version, Modflow USG. I'll show you an example of that. And then the most recent one is Modflow 6, which kind of combines a lot of features of the earlier models. There are a few other versions that have been released, but these are the ones that have been used most widely. The diagram I'm showing you here is a figure from one of the user manuals associated with Modflow, showing the different features or components that are simulated with the Modflow code. Modflow primarily uses what's called a finite difference model. The USG version, which we'll talk about in a minute, does a little bit differently, but a finite difference model version, the main version, uses what we call a Cartesian grid. Cartesian meaning it has rows, columns, and layers. So the rows start at the top. The numbering starts at the top and increases as you go down. The column numbering starts at the left and increases as you go to the right. And then the layer numbering starts at the very top layer, and as you go down from top to bottom, that's the direction of the numbering, so as shown here on this diagram. Each cell, therefore, has an I, J, and K address, representing I representing the row, J representing the column, and K representing the layer. And each cell can have its own properties, such as hydraulic conductivity, and it also has its own width and thickness and length. And so one of the ways to think about this is it's orthogonal in the x and y direction, but the thickness varies in the z direction. So if you look down on plan view, while the row and column widths can vary, it goes straight. There's only one width for each row, or height for each row, and one width for each column. But in the z direction, there can be an independent thickness for each of the cells. And so you get what's shown here. Now this first diagram I showed you, each cell in a particular layer has a uniform thickness, but in reality that vertical thickness in the z direction can vary from cell to cell. But again, each row has a uniform height, each column has a uniform width in the finite difference version of Modflow. Now, in recent years, there's been a new version of Modflow that uses what we call an unstructured grid. It does not have rows, columns, and layers. There are a number of ways that you can formulate the cells as shown in these different diagrams. Each cell can have any number of sides to it, and all you need to define is for each cell what are its adjacent cells. You can even, as shown in the lower right there, you can even have two cells adjacent to one side of the next cell, and so you can really do some elaborate things. The primary motivation for Modflow USG is that it allows you to refine the grid and have much smaller cell sizes at the locations in your model where the head is changing most rapidly. So next to a well, or next to a surface feature, a source sink such as a river or a spring. And at these locations, the water table or the head can change rapidly over a short distance. And to accurately simulate that, you need to have smaller grid cells. Well, if you're using this Cartesian representation, if you want to have a small grid cell at some point, you have to extend that small size over the entire row and column that it intersects with, so if you have a bunch of locations where you want to have a really fine grid resolution, you end up with having to have that same grid resolution over a large part of your grid. But with the unstructured version, it allows you to localize that, and it's a much more efficient use of your memory, and you can get a pretty high accuracy with a relatively small number of cells. And so it's a pretty significant advance. It does make the construction of the grids a little more complicated. There are nice tools in graphical user interfaces such as GMS, which we'll be using, that automate this. But it is more complicated. We will not be using Modflow USG this semester. I consider that an advanced topic. So we'll be focusing exclusively on just the regular version of Modflow that uses a Cartesian grid. Okay, this is the governing equation solved by Modflow. Same one we saw in one of our most recent lectures. The Modflow documentation uses a little bit different notation. These are still second derivatives, but it shows it as a derivative of a derivative. But it's the same thing. It has kxx, kyy, kzz, indicating that You would have the full hydraulic conductivity. If you had the full hydraulic conductivity tensor, you'd have the cross derivative terms, but we don't have those. And therefore, one of the primary assumptions associated with Modflow is that your let me back up a little bit, that your rows, columns, and layers, those orthogonal directions, are aligned with the major and minor principal axes of hydraulic conductivity. And that's how we get rid of the off-diagonal terms. This W term represents sources and sinks. Sometimes we've shown it on the opposite side with a positive notation. You can put it on either side, it doesn't matter. And then, of course, we have the transient term on the right. So let's talk about Modflow organization. This diagram shown on the right was a graphic that was on the original Modflow User's Manual back in 1983. The MOD part of Modflow stands for modular. The idea is that you have different components of the model that you plug in and use on an as-needed basis. So if you want to simulate rivers, you plug in the rivers package. If you want to simulate drains, you use the drains package, and so forth. And this modular structure makes it possible to add new features as time goes on. And that has happened over the years. A lot of new features have been added to Modflow based on its the manner in which it was originally constructed. And then several years after it came out, they came out with this new concept of a process. And so the major tasks associated with Modflow are organized as processes. So there's a flow process. There's actually a transport process for contaminant transport. It's not used much. And there's an observation process we'll talk about. And then, but primarily we use the flow process, and within each process, more specific tasks are performed by what are called packages. So a package simulates a very specific feature or element of your groundwater flow system or of the solution. Each package has its own input file, and there's a place in the main input file where you designate which packages are being used, and then it knows to look for each of the individual package input files. And so we'll be talking a lot about packages over the next little while, and of course each process could then therefore use one or more packages. So the global process, this is one of the main processes that is used no matter which set of packages you're using. And one component of the global process is the spatial discretization. So basically the definition of your grid, the number of rows, columns, and layers, the thicknesses of those rows and columns, and the top and bottom elevation for each cell, or the thickness of each cell. So the grid configuration and geometry are defined as part of the global process. Furthermore, the time domain is defined in the global process. So this would be what we call temporal discretization. So how do you divide the simulation time? If you're going to do a simulation of how the aquifer responds over a 10-year period, then you would first subdivide that 10-year period into a number of stress periods, which are periods over which your inputs can change, and then within each stress period you may have multiple time steps or computational intervals. And we are going to revisit this later in the semester when we're going to spend a lecture specifically talking about doing transient simulations, and we'll cover this in more detail. The global process also defines the units you're going to use, feet versus meters, seconds versus days, etc. And also this is where you indicate which packages that you're going to use in your simulation. There's also a groundwater flow process where we formulate and solve the groundwater flow equation using the finite difference method. So this is the main part. Once you've established the geometry and properties, this is where you define the hydraulic conductivity, the aquifer properties, but also the boundary conditions, the sources and sinks. And so this is a primary part of the Modflow code. And it includes what we call flow packages, which we'll talk about later. A flow package is where you define basically what you need for Darcy's law, the hydraulic conductivity and storage coefficients. And then it also is where we solve what we call our source sink packages, rivers, wells, recharge, and so forth. And where it also includes a solver. Once you've set up the equations, how do you go about solving them? And then finally, in terms of processes, there is the observation process, which we use for model calibration. And what it does is you input a set of observed heads and at individual points or cells in the grid, and you can also input observed discharges or gains or losses or gains from rivers, streams, lakes, and so forth. And then the observation process will calculate model simulated heads and flows at these locations and compare them to what you've entered from field observed values, and it will generate a very rich set of statistics to tell you how well calibrated your model is. So it's used to automate the model calibration process, and it can be really useful. So that summarizes the main processes. Again, we have the global process, the groundwater flow process, and the observation process. So now let's talk about packages. There are a set of packages which are required, meaning you always have to use them. One of them is the discretization package. This is part of the global process. It's where you define your rows, columns, and layers. There's also a basic package, as it's called, and this is where you define the active, inactive regions of your model. And we're gonna have an example of that in the next slide. You also input the starting heads. Modflow uses an iterative solver, and so you have to give it an initial guess for each cell. What is a guess at what the head is? It doesn't have to be accurate, it just has to have something to start with. And there are ways to automate that, which is nice. Another required package is called output control. Basically, this is where you define what features of the model that you want to be written to output files and at what frequency. Well, why doesn't it just write out everything? Well, you could end up with gigantic output files, and it slows down the process a little bit. So, generally you use some care and consideration in determining what you want to output. And then you need to select at least one of the flow packages. And there we have the block-centered flow, BCF, layer property flow, LPF, hydrogeologic unit flow, HUF, and upstream weighting package are four flow packages. The little asterisk there by the LPF package means that's the default one, and that's the only one that we're going to be using this semester. The others are the BCF is kind of an older one that you don't see much anymore, and the other two, HUF and UPW, we actually will use UPW a little bit, but those are much less commonly used. Typically we use the layer property flow package, and basically the main thing you do in a flow package is define your properties, hydraulic conductivity and storage coefficient. And then you also need to select a solver. Modflow comes with a whole suite of solvers. And these are basically different algorithms for solving the equations that are formulated using your inputs and your boundary conditions. It comes up with this giant set of equations, linear equations that then have to be solved. And each of these different packages uses a little bit different algorithm. Why do we need multiple solvers? Well, some are faster than others, but some of them, sometimes you'll encounter a problem where a solver just fails and it can't find a solution, so you pick a different solver, and a lot of times it works great. So there are good reasons to have multiple solvers. PCG stands for Precondition Conjugate Gradient, and that is the default one, and that's the one we will use most this semester. We are going to have a lecture later on where we talk about each of these solvers, the advantages and disadvantages, and how to use the solvers and navigate them. Okay, I'm going to jump back here to the basic package, this I-bound array. What is that? This defines your active and inactive zone. So let's suppose that you have a grid like this, and you need to simulate an aquifer with the shape shown by the red line. So basically what you have to do to get that proper shape is you take all of the cells that are outside that model domain and you mark them as inactive, and the models that are inside that domain you mark them as active. And this is controlled through an array of integers called the I-bound array. And typically the values are 0, 1, and -1. Technically it's positive, 0, and negative, but usually people use 1, 0, and -1. And so 0 means an inactive cell, so all those that you know, in this outer part that we turn on and off, those would be marked with 0. The ones inside the polygon would be marked with a 1. And then a -1 is a special case for applying a specified head or a constant head boundary condition. If you mark a cell with a -1, it means it's active and it's also a fixed head cell, meaning that the head is fixed and it doesn't vary and it becomes a boundary condition. So you would use this to identify cells associated with a very strong source or sink, like a large river or a lake, can be simulated using a specified head boundary condition. So here are some examples. This is a model that I worked with my colleagues at Aquaveo. They did most of the work, but this is a groundwater model used by the state of Virginia for a number of years to simulate the impact of various groundwater withdrawals in their coastal aquifer. And the main grid is shown here on the left. You can see those boundaries, and then this dark boundary here represents the active zone at a certain depth. But as you go from one layer to the next, this was if I recall correctly, it had like 10 layers in it. And as you go down through the model, the active zone changes from layer to layer. And so on the right, you will see the active zone at one particular layer in the model. And again, that is all managed by the I-bound array as you move from one layer to the next. Okay, as I mentioned, you do need to select one flow package, and there are 4 options as I described before, and this is for defining the flow properties. And the layer property flow package, the LPF package, you enter for each cell, it says for each layer, but you do it on a cell-by-cell basis. You enter a KH, which stands for horizontal hydraulic conductivity, and a KV. So the KH would apply for both X and Y. And then KV is your vertical hydraulic conductivity. And you can also input storage terms of storage coefficient, which we'll talk about later when we get to transient models. The vertical hydraulic conductivity, you can either enter that directly as a unique value, or you can give it a ratio that varies based on vertical anisotropy. So, for example, you could say, well, my kV is always 1/5 of my kH term. So then no matter what kH you enter, it just automatically scales it by a factor of 1/5 to get kV. And so that can be a really useful way to define that. And now the kH term is use the same horizontal hydraulic conductivity for both the row direction and the column direction. However, you can input what's called a horizontal anisotropy term, which the default value is 1, but if you change that to say 1.5, then you can have the the hydraulic conductivity in the y direction, or in the along the rows the column direction, be different from the row direction. And so that's something that you can do with this package as well. You can also define the layer type as either a confined aquifer or a convertible aquifer. Convertible means that it starts out saturated, but it could potentially become unsaturated or partially saturated if the water table drops below the top of the cell. You can make all of your cells convertible. That's the general case. The advantage of identifying some as confined: if a cell is a confined layer and it's going to be saturated through the entire simulation, it can use a little bit faster solution that uses a linear solution instead of a nonlinear solution to find that. And if you have an unconfined aquifer, then by definition it's convertible because the water table elevation is below the top elevation of the cell. And this is something we'll learn more about through practice and through use. And then we have the optional packages. So this is not a complete list. There are actually quite a few more, but these are the ones that are most widely used, and just a set that I picked that I encountered a lot. Some of these are used almost all the time, such as the well package and the recharge package. It's very rare that you'll have a model that doesn't at least use the recharge package. Each of these can represent different features. And we're not going to discuss all of these, but we will discuss most of these in our subsequent 2 lectures on the optional packages. So there you have it. That is an overview of Modflow and its organization. Remember, we have processes and then packages, and we have both required and optional packages. This is a lot of material, but this is meant to be an introduction. As we go through our examples exercises and homework that we work together, this stuff will become kind of second nature to you over time and repetition. But this provides kind of an introduction and overview you need to get started. Thank you.